Let's look at a couple of equations that can help us understand why the eye wall has to be bending outward and give us this so-called stadium shape to the cyclone inside. So let's look at the specific angular momentum. So it's absolute specific angular momentum in a open system like the atmosphere and ocean. You typically look for angular momentum of a parcel of air or water because that's the only thing you can do. So here we write it as r cross VA, where VA is the absolute velocity, and momentum then can be written as RV. V is the rotational speed, and F0 r squared over 2, which is a contribution from rotation and the Coriolis, right? So as r increases away from the eye of the cyclone, this term is going to add to the angular momentum. But if you go in the vertical, dV/dz is less than 0 because the fastest wind speeds are near the surface, so the angular velocity is highest at the lower levels and decreases as you go up. So dm/dz then becomes less than 0 if you remain at constant r. But as we said, to see if the tilting eye wall and the equivalent potential temperature surfaces are angular momentum surfaces, then you can see whether angular momentum in this adiabatic system can be maintained and how it can be done. So if you can add to the m with F0 r squared over 2 as you go from the surface to above for a parcel. So you move the parcel away from the axis of rotation and increase r and compensate for decreasing v term. So rv decreases, but you add F0 r squared, so then you can conserve angular momentum. So dm dr is greater than 0, and that together gives us the confirmation that in fact the eye wall is a angular momentum surface. So that confirms the theory that we already discussed. The utility of potential intensity is also visible in understanding tropical cyclones. So here the maps of mean minimum sustainable surface pressure, which is obviously a measure of potential intensity, is shown for climatological sea surface temperature conditions for February and for September. It's the mean over 1982 to 1995, and you can see that in February sun is getting closer to the equator, so the sea surface temperature distribution is quite different than here because you have the sun over in the northern hemisphere starting to move back towards the southern hemisphere here. So you see more of a symmetry here than here. Nonetheless, the minimum sustainable surface pressure here is 840 hectopascal, and here it is at 870 hectopascal. So obviously this depends on La Nina, El Nino, and whether the El Nino is warming in the eastern Pacific or central Pacific, and so on. Okay, we looked a little bit at that on how the different flavors of El Nino affect cyclogenesis and so on. So this is another usefulness of defining potential intensity so that you have a good idea. It can also be used to see how real cyclones compare to these potential intensities and theoretical maximum velocities that the cyclones can accomplish. So here we are looking at normalized wind speeds. So cumulative density functions for normalized intensity, so actual divided by potential for tropical cyclones in the North Atlantic and Western North Pacific. Data are stratified by storm intensity. So you can see that the tropical storms are on one probability distribution here, and hurricanes are on another, and here the same thing, tropical storms, slightly different of course because it's a different system in terms of the shear sea surface temperature and the seeding processes easterly waves versus MJOs, equatorial Rossby waves, Rossby gravity waves, and so on. And the typhoons, again, slightly different. You can see the hurricanes here have larger ratio of normalized wind speed. Nonetheless, the observed storms have an equal probability of being somewhere once a tropical storm is formed. If they go to a full hurricane, they're going to end up here, or they're going to be somewhere in the middle. So they have an equal probability, two distinct probabilities as a tropical storm versus a typhoon or a hurricane. So this is another usefulness of the idea of potential intensity. Okay, what is the maximum intensity that a tropical storm can get, or what it can reach if it becomes a hurricane or a typhoon. So there are two different but equal probabilities for all storms and hurricanes, and the observed intensity is going to be somewhere in the middle. Okay, or along that line. The other usefulness, of course, is to look for how the evolution of potential intensity affects or is occurring. So here, evolution of potential intensity anomaly, so deviation from the long-term mean over 1985 to 2002 for all northern hemisphere tropical cyclones. MPI anomaly is so mean potential intensity anomaly is relative to a 17-year mean of PI calculated over 1985 to 2001. This mean PI reflects the climatological spatial variation in sea surface temperature and tropopause base states. So that's our thermodynamic constraint that we talked about. All times for all storms south of 35 north and of at least tropical storm intensity are included. Climatological and anomalous PI are calculated on a 5 degree by 5 degree grid. Days relative to TC arrival refers to the passage of a tropical cyclone into a 5 degree by 5 degree grid box over which PI anomaly is calculated. So here is the day 0, where you are looking at different cyclones and tropical storms and different regions of the northern hemisphere, and you are looking at days before the tropical storm arrives in that box and days after. And you can see that for tropical storm, here is the MPI anomaly, and basic idea is that there is a spin up before the storm arrives, and then in terms of the hectopascal pressure anomaly, and as a potential intensity anomaly, and it persists for many days, almost 2 months here, and the scale of the PI is much higher, of course, the anomaly for category 1, 2, and category 3 and 5. So basically the cyclone impact on the atmospheric system can last for a long time, because cyclone is part of this environment and it has so much energy that even though it is being steered by the environment and can be affected by the environmental shear and so on, once it becomes a tropical storm from a perturbation or a category 1, 2, or 3, 5 cyclone, then it's going to have a significant effect that's going to last for a long time. So in that sense, the steering winds themselves are determined by the cyclone itself affecting the steering in combination with the environmental winds. On the ocean, you can see here there is a cyclone, I forgot which one that is, a typhoon. You can see that it's starting here in August 20th. As it strengthens, it's beginning to cool and fracture the warm pool that is in the north in this season, and leaves a clear cold trail all along the way. We know that the winds are strong enough to mix the ocean down to several hundred meters, 200 to 300 meters, and pull up cold waters and leave nice well-mixed waters. And there is some nice study on this by I think Wilco-Haselege, about how much heat flux is occurring because of storms like this, even though he does it for, I think, mid-latitude storms. Nonetheless, same idea. Sst Anomalies, again, looking at when the storm is entering the box. Before, you can see there are smaller anomalies associated with the storm or the cyclone arriving. So it is SST here and the 100 to 200 hectopascal thickness, and you can see that depending on the category, whether it's a tropical storm or category 1, 2, 3, 5, and unlike the difference here in MPI, the SST anomalies are not that different. So ocean is inertia is much higher, density is much higher, heat capacity is much higher, so the mixing and the cooling effects are different once you go from a tropical storm to cyclone, but the category of the cyclone doesn't seem to matter that much. But again, the time it takes for the anomalies to return back to normal takes more than a month here, and the atmosphere, which is much lighter and has much lower inertia, you can see adjusts back much more faster here in this case in terms of the this is 1000 to 200 hectopascal, so essentially surface to the upper atmosphere. Tropical storm has a much smaller perturbation, and 1 and 2, 3 and 5 have larger and bit of a difference there as well in terms of meters of change in the thickness. But you can see that as the storm passes, within a couple of weeks the system is adjusting back to the pre-storm conditions. Okay, so it's a Lagrangian system that's moving, and it's perturbing the atmosphere along the way from the surface all the way to the top, but then it adjusts back quickly as the storm passes. Okay, so that's an example of how potential intensity can be used to understand the impacts on the ocean, on the atmosphere, and so on.